differential equations and how to solve differential equations using the variable separable method and the direct integration method. So let's just see what the differential equation is. In simple terms, a differential equation is an equation which involves the derivative terms. It can be the first derivative, the second derivative, or any other higher derivative. If an equation involves dy by dx term, a first derivative, or d2y over dx squared, a second derivative term, the equal sign, and another expression on the right hand side, it is called a differential equation. So it simply states how a rate of change or a differential in one variable is related to the other variable. So dy by dx means in a derivative term how the variable y is changing with respect to the change in the variable x. A differential equation is any equation which contains derivative terms, as I have already explained. And there can be ordinary derivatives or the partial derivative, but we are going to pay our attention only for ordinary derivatives. So for a differential equation, the solution is not a single value like for a quadratic equation. It's a function. You can't find a single value. As the solution, you may get another function involving the independent variable of the differential equation. So first we need to know what the degree and the order of a differential equation is, because the method of the solution depends on the order and the degree of the differential equation. If the order is equal to 1, we call them the first order differential equations. So we are going to learn about these first order differential equations. And if the order is 2, it is called a second order differential equation. So we have different methods of solving first order differential equations and a different method for solving second order differential equations. So it is important to understand the order and the degree of the differential equation. So first we will consider order. Order means a differential equations can be classified with respect to the order. So the order means the order of the highest derivative present in the equation. If we take this example, here in the first term, in this equation, the first term is the third derivative. In the second term, we have the first derivative squared, and on the right hand side, we have the second derivative. So we have a first derivative, a second derivative, and a third derivative. So the highest order derivative present in this equation is the third derivative. So we say the order of this differential equation is equal to 3. Degree. The power of the highest order derivative is called the degree of the differential equation. So if we consider the same example, here the highest order derivative is the third derivative in this equation. So power of this highest order derivative is equal to 1 because this term is not raised to any higher power. So we say this has degree 1. So I have given some exercises for you to find the order and the degree. Right? And I have given the solutions in a separate document. Right? So I'll explain just 2 from this exercise. Right? So finding the order and the degree. So the first differential equation is we have d2y over dx squared to the power 3 plus dy by dx equals sin x. So first we should find the highest order derivative of this equation. The highest order derivative of this equation is the second derivative. So we say the order is equal to 2. Order is equal to 2. Or we can say this is a second order differential equation. Then what about the degree? Degree is the power of the highest order derivative. The power of the second derivative is equal to 3. So we say the degree of this differential equation is equal to 3. Let's take another example. So in this differential equation we have d3y over dx3 plus x squared d2y over dx squared to the power 3. So we have a third derivative term and the second derivative raised to power 3. So the highest order derivative present in this equation is a third derivative. So we say the order of this differential equation is equal to 3. Then to find degree, we have to find the power of the highest order derivative. The power of the highest order derivative is equal to 1. So the degree is equal to 1. So you can find the answers for the remaining exercises given in the lecture note in this document. So let's go to another classification of differential equation as linear and nonlinear. So a differential equation is said to be linear if it satisfies these properties. The dependent variable and its derivatives are of degree 1. Degree 1 means it is not raised to any power. So if we say we have the derivative term dy by dx, the dependent variable is y. So the dependent variable and its derivatives are of degree 1 means in the differential equation we cannot have terms like y squared and dy by dx squared d2y over d3 d2y over dx squared raised to power 2. So if we have such terms, then it is a nonlinear differential equation. Then the second property is dependent variable and its derivatives do not occur as a product. That means you cannot have terms like y into dy by dx because there you have a product of y and its derivative dy by dx. Third property is they should not involve nonlinear functions of the dependent variable. That means you can't have terms like y squared or any trigonometric functions of the dependent variable like sin y, cos y or tan y, any trigonometric functions because they are all nonlinear functions, and log y or exponential y, any nonlinear function. You cannot have any nonlinear function of the dependent variable. But if you have nonlinear functions of the independent variable like sin x, cos x, and exponential x, right? If we have such terms or such functions of the independent variable, then they become linear differential equations. So they are considered as linear differential equations. If we consider this example here we have d2y over dx squared plus 3 dy by dx minus 9y equals 0. So this is a linear differential equation because all these terms we have degree 1. If we consider each of the terms here, we have 3 terms. For all 3 terms, the degree is equal to 1. If we take the second example here, you can see that this dy by dx term is raised to power 2. So it becomes a nonlinear differential equation. This is nonlinear. The reason is the degree of second term is not equal to 1. It is equal to 2. Then this is the most important part, how to find the solution of a differential equation. The solution is found when we can obtain an expression with a dependent variable in terms of the independent variable. That means for the differential equation involving terms like dy by dx plus 3 times d2y dx squared, if we have a differential equation in that form where the dependent variable is equal to y and the independent variable is equal to x. If we can find an expression for y in terms of x, which is the independent variable, it is called a solution of differential equation, and the solution should satisfy the given differential equation. So in this exercise, before we find the solution for a differential equation, we should be able to find whether a given function satisfies the given differential equation. So here y equal e minus x plus 1 is the solution of y dash plus y equal 1. So you have to verify that these functions are solutions, whether these functions are solutions or not. If these functions are solutions of differential equation, they should satisfy this given differential equation. So let's take a look at how to verify that the given function is a solution of differential equation. Okay, let's take a look at this one. So this one, the third one is that. So here, the function is y equals 5 e2x, and the differential equation here, I'm talking about this third one here. This is a solution of this d2y over dx squared minus dy by dx equals 2y. So let's check whether this solution satisfies this differential equation. So in order to substitute this solution or the function into this differential equation, we should find the first derivative and the second derivative. So let's take the left hand side of this differential equation and check whether it is equal to 2y. So if we differentiate this one, if you find the first derivative, dy by dx is equal to 10e2x. The second derivative is we have to differentiate this exponential function again, which is 20e2x. Then if we take the left hand side of the differential equation and substitute these two, we have 20e2x minus 10e2x, which is equal to 10e2x. And this can be written as 2 into 5 e2x. So it is equal to 2 times y, because this part is equal to our function y. So this is equal to the right hand side. So we can say this is the solution of the differential equation. So for a differential equation, we have two types of solutions. One is called the general solution and the other one is called the particular solution. So there are cases where a differential equation can be satisfied by more than one expression. For an example, if we take this differential equation where dy by dx is equal to y, that means the derivative, the first derivative is again equal to the function itself. So this can be satisfied by this function y equal ex. You know the derivative of ex is again equal to ex. Or if y equal 2ex, so this here the exponential function is multiplied by a constant. So if we find the derivative of this one, again the derivative is equal to same as this function. Or y equal 3 over 4 ex. So this 3 over 4 is the coefficient. And many other functions of this type. So we can say the general solution of this differential equation is equal to y equal the constant times ex. So this arbitrary constant can be found only when we have some additional information. So a solution which all possible solutions can be found is called the general solution, because by substituting different values for a, we can find different answers. If we say a is equal to 1, we get the first answer. If a is equal to 2, we get the second solution. If a is equal to 3 over 4, we get the third solution. The general solution means when we can't find this constant, because this is an arbitrary constant. So in the general solution, we have arbitrary constants y equal to a x, where a is any constant, is the general solution of dy by dx equals y. Then the particular solution. The particular solution means simply if you can find a particular value. Here, for an example, if you can find a particular value for this a, depending on the conditions given, it is called a particular solution. So if we take these three solutions separately, this can be considered as one of the particular solutions. Because we have a specific value here, we have a specific value for a is equal to 1. In the second solution, y equal to e, x, a is equal to 2. So we have a particular value, we have a specific value. So if we have a specific value, it is called a particular solution. So to find the particular value, that means to find these arbitrary constants, to find the value of the arbitrary constant, we need some additional information. So this additional information can be in the form of the boundary conditions or the initial conditions. So the difference between the boundary conditions and the initial conditions is if we have two conditions, like for a second order differential equation, we need two conditions in order to find the arbitrary constant. If we have two conditions, if both conditions are given at the same value of x, it is called an initial condition. In common, we can say the conditions are boundary conditions. That means in common, we can call the conditions as boundary conditions. So in this example, you have to verify that this given function is a general solution because we have two arbitrary constants, and verify that this is a solution of this differential equation, and then find the particular solution. Means you have to find the value of a and b using these two conditions. Without these conditions, you can't find the values of these a and b. So what are the conditions? It gives you the y value when x is equal to 0, y is equal to 0 when x is equal to 0. So the second condition is the first derivative is equal to 0 when x is equal to 0. So we need two conditions because we have two unknown constants in this solution. So let's see how to find this particular solution, and first we need to do the verification part. So this is the solution. For the verification part, we have to substitute the solution into our differential equation. So for this, before substituting, we need to find the first derivative and the second derivative. The first derivative is 5e2x over 2 plus a. The second derivative is 5e2x. So we take the left hand side. The left hand side is d2y over dx squared, which is 5e2x. So we can say this solution satisfies the given differential equation, and then we have to find the particular solution. That means we have to find the values of a and b. So to find the particular solution, we will substitute these initial conditions. The initial conditions are when x is equal to 0, y is equal to 0. So substituting this point to the solution, we have y equal 5e2x over 4 plus ax plus b, and then substituting x equals 0 and y equals 0, we have 0 equals 5 over 4 is 0 plus b. So b is equal to minus 5 over 4. Then using the second condition is the first derivative is equal to 0 when x is equal to 0. So substituting this condition, substituting the above value for the first derivative, dy by dx equals 5e2x over 2 plus a. 0 equals 5e0 over 2 plus a. So we can find the value of a as minus 5 over 2. So the particular solution is y equals 5e2x over 4 minus 5 over 2 times x minus 5 over 4. So this is the value of a and this is the value of b. And then we come to solving differential equations. Solving differential equations. So in solving differential equations, we are going to look at two methods. There are many different methods of solving differential equations, even the first order differential equations. So we are going to consider the most basic forms. The first one is the direct integration method. This direct integration method can be used if the differential equation is in this form, if we can express it in the form dy by dx equals fx. So that means dy by dx equals, in the right hand side we have only terms involving x. So this is an exercise given in this form where you can use direct integration to find the solution. So all you can see for all these differential equations we have functions involving x only. So the first one is dy by dx equals 2x squared minus 3x plus 3. And to find the solution, if we know the derivative of this function, how to find this y? How do you find this function y? Then you have to integrate this function here, because we have to reverse this differentiation process. To reverse the differentiation process, we need to integrate this one, that is 2x squared minus 3x plus 3. Integrate this one. So using the standard integrals, we can find an expression for y in terms of x. So this is called the general solution of the differential equation, because we have arbitrary constants. So let's take a look at another example. dy by dx equals 3x plus 2. So if we integrate this one, 3x plus 2, then we have 3x squared over 2 plus 2x plus c, which is the general solution. So if we take a look at the fourth question, in the fourth one, you are given the second derivative. d2y over dx squared equals 5a2x. So if we integrate this one only once, then we get the first derivative. So dy by dx is the integral of this one, which is equal to 5a2x over 2 plus c. To find y, we have to integrate this one again. So that means if we have the second derivative here, we have to integrate it twice to find the function y. So to find y, we have to integrate this function here, 5a2x over 2 plus c. By integrating, we have 5a2x over 4 plus cx plus d. So we have two arbitrary constants as c and d. So for a second order differential equation, we get two arbitrary constants in the general solution. For a first order differential equation, we have only one arbitrary constant in our general solution. So the next method is the separation of variables. The main objective of this technique is we can rearrange the equation so that we have all terms involving one variable in one side and all the terms involving the other variable into the other side of the equation. So suppose we have a first order differential equation of this form: py dy by dx equals qx. So qx and py are functions involving x and y. That means qx is a function involving x. So that means we have all x terms here. And py means functions involving y. So we have all the y terms. So for an example, this is a separable differential equation, because we have y squared dy by dx equals 1 over x to the power 3. So y squared means it's a function of y. This is a function of x. So this can be considered as qx and this can be considered as py. How do you find the solution for this kind of differential equation? So we can solve it by separating the equation into two parts. We move all the equation involving the y variable into one side and all the equation involving x variable into the other side, and then we integrate both sides. If we take this one, this is general form of a separable differential equation. So we integrate the left hand side with respect to y, because py means terms involving y, so we can integrate only with respect to y. On the other side, we have x terms or the x terms, so we have to integrate with respect to x. We have given an exercise to find the solution. All these differential equations are separable differential equation. So let's take a look at one or two examples. Separation of variables. The first one, we have to integrate this one with respect to y squared, and 1 over x to the power 3. So this is the function involving x. So if we integrate the left hand side, we get y to the power 3 over 3 equal the right hand side, we have x to the power minus 2 minus 2 plus c. So this is the solution of the differential equation. We have y equal an expression of x. So when we say the solution should be a function of x and y, that means we should have a connection between y and x. Then the left hand side, it is not necessary that you should have y equals some terms involving x. You may have different forms of y, like y squared, 1 over y, log y, right? So different forms of y. It shouldn't be like y equal terms involving x. So here the solution is y to the power 3 over minus 3 over 2x squared plus c. Another example, here you have to separate the variables first, because this y square should be taken to the left hand side, and here we have x minus 3 over x to the power 3, then we have to integrate. So integrating both sides, left hand side with respect to y and the right hand side with respect to x, we can find the solution. So here I have given the solutions for all the exercises given in this note. So that's all for differential equations. So you should know that there are many other methods to find the solution of differential equations, that we have talked about only two basic methods to find the solution of just all differential equations.